Thanks for the introduction, Mark, and nice to be here. So I'm Jiajun. I started actually at Stanford, assistant professor of computer science at Stanford. I started 2020. So technically it's not that new, but because most of the time, we had pandemic and we had a building renovation, so it has to be remote. So I do feel pretty new in person at Stanford. Okay, so I mostly work on computer vision, AI, with some applications in graphics and also robotics. So I don't really feel like many people here probably know more robotics than me, so I would love to learn more from you, and please, any suggestions are very welcome. So I'm going to talk about multi-sensory neural objects. So multi-sensory, easy to understand. Neural objects, well, so what does that mean? I think people have been aware that there has been in some sense, you can call it like a big change or arguably a revolution in computer vision and graphics, that people have realized, oh, neural networks are powerful to representing shapes or representing scenes in general. But if you put them, historically, there has been mostly parameterized in explicit representations like meshes and point clouds. And then people are like, okay, what if we parameterize them using implicit representations, which has been another big family of object representations in graphics. But it turned out that for a long time, no one has really done that with neural networks. So people are like, what if we do neural networks for implicit representations? And that leads to a lot of advancements in vision and graphics, notable originally in geometry representation like DeepSDF, and later for appearance representations, which I think the most famous work is NeRF, right? So it allows you to synthesize objects in different views. And then people have thought, okay, now that it works so well in vision graphics, can it be applied in robotics? Now we try to do a little bit of work that as well. So here, today I'm going to talk about, in some sense, how we have been building these neural representations, but in an object-centric way. And I try to argue that why this object-centric way seems more right than just representing the scene as a NeRF and see how that can be used in robotics. Okay, so we want to model objects. Of course, that's very important, right? Manipulation, navigation, you want to recognize, find objects, interacting with them. And when you see an object like this, you want to model multiple aspects of it. You care about how it looks like, of course, the appearance. And by understanding how it looks like, that means you should be able to understand the object has geometry and textures, and you will be able to imagine how it should look like, from a different viewpoint. Right? So even just from very limited observations, you should be able to imagine the shape and textures of the objects, as well as if you really understand the materials of the object, how it reflects light, you should be able to synthesize the objects under different lighting conditions. So by the way, this is the output of one of our model, just going from a single image, it can do all these. But I'm not going to talk about it in this talk just because it's not related to robotics, but I have to talk more offline. So, but also at the same time, we care about how it sounds, right? So, this looks like pulse line. So if there's an impact on the object, or if I hit it, then you expect to hear sound like that. And the sound itself also gives you a lot of information about object materials. And if it's a dynamic scene, then about object motion as well. As well as how it feels, right? The tactile feedbacks and how it behaves. If I interact with it, if I push it, what's going to happen, right? Depends on the geometry, physical properties, materials, a lot of things. So that seems very important for a lot of applications, clearly in computer vision, but I feel like for object manipulation, it seems very important to model these objects in robotics as well. So if we look at existing object data sets, what are data sets there? There are data sets from the vision graphics community, like ShapeNet, which was also developed at Stanford. And it has all those geometries of objects with some texture variations. The nice thing is it does have a lot of variation in geometry, but the texture, because these are all provided by users, the textures here are pretty simple, so it doesn't really capture the distribution of textures of objects in real life. And it only has object visual appearance. It doesn't have anything like physics or materials and stuff like that. It has a little bit, but it's so little and so inaccurate that people don't really use them. So it's mostly about visual appearance. That means, okay, it's good for 3D reconstruction, but it's not good for manipulation because there's no physics. So alternatively, people like robotics, we're like, oh, we have real objects, right? They try to if we want to really standardize the benchmarking, then we should at least unify the set of objects that we care about. So there are benchmarks like YCB that you can purchase, and they ship you a set of objects that are supposed to be all the same. So that's nice. It's real. It's multimodal. But a lot of challenges, including every object is still kind of slightly different. Your box and my box are kind of different. And especially, I think, exemplified by this pandemic, that turned out to be really hard. Sometimes like you just cannot really ship them. There's like shipping delays, and there's a short in inventory. A lot of objects are missing, and they cannot be found anymore. So now you have to replace objects. So real objects, because they're real, they come with these real challenges as well. So we thought, is that possible for us to try to really think about what is the underlying physical models for these objects, and try to build models for themselves so that we can virtualize them, right? So that we can actually build virtualized set of real objects that they're so good and realistic enough that they're from real objects, so it does have not only visual appearance but also physics, and they're realistic enough that we can not only use it for vision and graphics purposes, but also for robotics purposes. So here, a very simplified version of the physical object model is, if you see an image like this, and you see there are 4 blocks, and that we see the image appear the way it is because there are underlying object physical states. Physical states include objects, and objects have their intrinsics, geometry, appearance, the materials of objects, mass and frictions. Their extrinsics, the positions and velocities of objects, and the scene descriptions, right? So scene descriptions, lightings and camera parameters, and all these things got put together, and because based on these scene states, they interact with each other. Eventually, it produces the image like this, right? So in computer graphics, the process is called rendering, right? It's kind of important subject in graphics. And more generally, you can call it simulation, because such kind of effect not only exists for a single image, it can apply for a video, and there could be dynamics going on as well. So now the question is, if we want to go from real objects to virtualize them, then essentially what you're having is images or videos or basically observations, mostly visual, can be multisensory observations of these objects. And now you want to think about, okay, then how can we get the underlying physical states of object, right? So that's like, you want simulated objects, but you don't want to create it from scratch. Like, okay, I sit in front of a computer and imagine what a chair will be like. I want them to be derived from real observations, like a real to sim process. So I want to invert the simulation, and how could I do that? So at a higher level, you can think about this. Yeah, we have object models, and simulation provides you and gives you sensory observations. But how can you invert this process? So most recently, we have seen there has been a lot of efforts in making things differentiable, right? To make this simulation process differentiable, right? Including as a nerve example that you try to make volume render differentiable. So it's actually making the rendering process differentiable. That is actually differentiable because that's based on how light travels, and that is something that you can write it down. And they're all linear algebra, so that's differentiable. And there's a little bit of 3D to 2D perspective projection as well. And of course, there are also other efforts in differentiable simulation in making dynamics differentiable, right? But of course, it's much harder because things like contact, it's not that differentiable, so you have to make approximations to it. And of course, people come up with all these different simulators, making different types of approximations to make them differentiable. Okay, but why do people spend so much effort in making these things differentiable? One of the reasons is, once it's differentiable, then we have seen neural networks that they can be updated, or you can do inference with backpropagation or gradient-based optimizations, right? So you can actually use gradient-based optimizations based on these differentiable simulators to invert the process, and you can get object models from these sensory observations. So that is like the hope or the idea behind this kind of work. So at a high level, you can think about nerve as one of the example as well. So for people who are not familiar with nerve, it is a method that takes in XYZ, which is the positions, and the viewing angles, which is the theta and phi, and try to gives you, okay, what will be the particular color, or they call it radiance, which is RGB, and the density, which is, you can think about it as approximation of geometry, but not really, the sigma. So you can get the radiance, color, and the density for any particular position and the viewing angle, right? So this is essentially a neural network that learns to parameterize the scene. So when you can query the neural network and saying, okay, please tell me what will be the radiance and density at this particular position if I see it from this particular viewpoint. And it can give you that information, and then when you can query multiple times, and you can put it together with volume rendering, but by making it differentiable. So you have trained a neural network to overfit the scenes, which usually means a lot of observations, like 100 images. But by feeding a neural network to these 100 images, the neural network learns the density and the radiance of every point and viewpoint in the scene. What it allows you to do is you can now see objects from different viewpoints. So here are some examples about what it can do, right? So here is like the output, right? So you have a lot of images and you can see it from different views, and these results are pretty impressive, especially given the scenes are complex and also they're all like in the wild real images. And again, this is back in 2020, so in the past 2 years, many of you may have seen a lot of advances since then as well. Okay. But the problem with NERF, especially if we think about want to apply it to robotics, I think a straightforward application is not that good or generalizable, mostly because I would say NERF is not really object-centric. Because if you look at what it's really doing, it is learning to encode, taking input XYZ positions and viewpoints and trying to output the density and radiance at that particular point from that particular viewing direction. So it actually learns to encode scene parameters that are not really belonging to the objects, like the particular lighting conditions. Right, so a NERF representation of a scene is specific and tied to the particular lighting conditions at that moment. Right, so it will not be able to tell you how would the object look like if I move the light, or if it's in the morning, how the object look like in the afternoon. Because all these other scene descriptions like lightings, they're baked into these object representations. Well, if you really want to care about building a physical object model, then you should model things that only belong to the object, right? Not modeling things that don't belong to the object, like lighting. So the parameters that NERF has learned, they're not intrinsic object properties, and they didn't allow you to do things like relighting. So more broadly, if you look at the type of NERF-related approaches for object appearance modeling, then they can broadly be divided into two categories. One is these NERF-related methods. They have very high fidelity biosynthesis results, but they cannot capture the object intrinsics, including their materials and reflectance, so they cannot relight the objects or do scene composition. There's another category of approaches which can be broadly refined to as inverse rendering methods. Then they do encode some of the object intrinsics that allows relighting, but so far the results are mostly assuming the object has very simple BRDF, which is think about it as a reflectance function. That is, how object reflects light, which is typically associated with the materials of the object. So they make very simple assumptions, like the object's Lambertian and things like that. So it cannot model things that are shiny, or it cannot model things that are translucent. So one thing that we did is, okay, can we try to think about learning these neural implicit representations that are object-centric? So what we learned is something we called an object-centric neural scattering function. So it learns the cumulative radiance transfer from an unobstructed distant light in addition to the volume density. So the function actually, so what it's really learning is you're not only having this output direction, okay, which point do I care about, and what is the viewing angle I have at this particular point, but it also cares about, okay, what will be the incoming light direction. Right, so the function now is higher dimensional, which means it's harder to learn, but it does capture what is really going on inside the object, right? Because now it has the lighting input, or the incoming light direction as an input, so it's conditioned on it. It's no longer assuming, the light is something that is within the scene, and it should just be baked into my object representations. But it only try to learn and focus on object intrinsics by making your learn function conditioned on input light direction and output viewing angles, as well as the particular positions on the object. And sometimes object can be complex, right? Think about a soap, which is translucent, right? Then the fact that it's translucent means there's a lot of things going on inside the object. Right? Lights are reflecting inside objects in very complex ways, and these things are really hard to model. So our goal is, we want to learn this transfer function that is at this particular point, given that particular incoming light direction and your viewing angle, what will be the amount of light or the percentage of light that got transferred, or I would say, to that particular outgoing direction. So hopefully the function will capture, without modeling what's really going on inside, it will learn, because these things are really hard to model. So we're saying hopefully it will learn to capture, complex lighting effects going on inside objects, but that's specific to the object. That's an object intrinsic property, and we want the neural networks or the neural network functions to overfit to that intrinsic properties instead of the general lighting conditions or scene descriptions. So specifically, the OSF looks like, you have spatial locations just like NERF. You have distant light direction, which is where the light is coming from. And you have an outgoing light direction or your viewing angle. So the first and second are same as NERF, but now you have this incoming light direction. And the output is this radiance, cumulative radiance transfer function and the density function. So density is the same as NERF as well. Okay, so look at what's going on is, you have the light, and then you have these particular positions, and you want to compute, okay, to what extent is the light in this particular incoming direction get reflected to that particular outgoing direction, right? So so essentially you're having the amount of light that got multiplied by this transfer function, which is essentially like a coefficient, and that should be the outgoing light. So because the output format, in some sense you can see it's kind of very similar to the standard volume rendering framework as used by NERF as well. So it still allows you to use volume rendering to learn from images. So that's the same as NERF. But because you are overfitting to these object intrinsic functions, you can now approximate the appearance of both complex objects, their reflections properties, and for both translucent and opaque objects. So here are some examples about how we were able to relight opaque objects. And the first is ground truth, the second is our reconstruction. I can rotate it, and you can see the reconstruction. And if you compare with standard NERF-based methods or some extensions to it, like the inverse rendering methods I talked about earlier, then you can see our results look much better. And here are some more results as well. You can see it can do novel view synthesis, it can do relighting. So you can rotate objects, you can relight objects. And for both novel view synthesis and relighting, it does much better than the baselines. And here's an example of a translucent object, which is Stanford bunny. Right, so you can relight the object, but also capturing the complex inter-object reflections. And again, that's better than baselines. And while these objects are, synthetic, here are some results on relighting a real object. So we actually purchase some soap, and then we try to think about how the model performs if you have this real objects, which is soap, and you can synthesize it from different views as well as relight objects. Yeah, the relighting is kind of a little bit subtle, but hard to see. But because the soap itself is translucent, but mostly opaque. And by learning things that are object-centric, what you can do is you can think about if I have one OSF for that particular object and the other OSF for a different object, and they're all modeling how objects reflect light. So you can put them together with standard ray tracing, and you will be able to seeing scenes composed of multiple objects learned by our OSFs and relight them. Well, if you just standard put multiple NERFs there, then first it doesn't support relighting, right? So you cannot really see the shadows moving as the light move around. And second, the quality is not as good. Okay, so this is a kind of a high level about how it looks like, our efforts in building these neural representations for objects and try to think about how it looks like so that you can do novel view synthesis and relighting. But what about sound? Can we do similar things for sound? So we said we want to think about and leverage what is the physical object models for these objects. And for objects' visual appearance, it's their geometry and it's how they reflect the light, the BRDFs. So we try to model that, right, so that we can disentangle the lighting conditions. But what about object sound? What are the physical model for the sound that the object makes? So if you think about the intrinsics for sound that object makes, then objects make sound because they vibrate. Right, so if you think about why the sound, this is like a metal, object, and for the sound it makes, it's making that sound because it's vibrating in these different modes. You can actually visualize them. So the sound of every object can actually you can write them down as a modal model, where the sound of object is composed of a number of different frequency modes with different gains and damping. And they got put together, and of course this is kind of approximate, but essentially that's how the object is making those sound. So similarly, this is like a simulation process for the sound the object makes, just like rendering is, you can think about it as a simulation process to give you the appearance of the object. Then now the question is, yeah, is it possible for us to also make that differentiable? Well, it turns out this is differentiable too. So this is joint work with Dr. James and Jeanette Borg at Stanford at last year's Coral. So what we did is, once we assume we have the frequency modes of objects and how they vibrate, and for each vibration mode you have the corresponding damping coefficient as well as the gains, then you can write it down and make the whole process differentiable. So what's going on here is if you have a ceramic mug, you can have an impact hammer and you can collect the sound that it makes. And because now you know, right, why the object is making the sound the way it is, and you can write down this forward model or simulation model and you can make it differentiable. Then what you can do is now you can actually optimize or search for the impact forces as well as the impulse responses. Then in the forward model, okay, if I put an impact force here, and then I will get a particular impulse response. So I can convolve the two, and then that will be okay, this is my synthesized waveform, assuming that will be the top is my impact forces, I would say the interaction profile, and you can render that in a differential way to the spectrogram under this particular condition, and compare that with what you actually observe. Right, think about it. Now, in NERF, you have a number of images, and you want to invert this differential rendering process. You get geometry and radiance. Right, in OSF, you have a number of images, and you want to invert that. Now you condition lighting, so you want to invert that and get the reflectance functions, or the radiance transfer functions. And here, you're not seeing the objects, but you're hearing the objects. What you observe, it is ground truth or the actual observation of the spectrogram of the object. And you want to invert this process by searching for the forces and the way you interact with the objects by convolving the interaction profile with the impulse responses. Then you get this synthesized or simulated waveform and the spectrogram, and the goal is to make the two match. And because the whole simulation process is now differentiable, as I said before, you can now do a gradient-based update. Right, so you can actually just do gradient-based optimization to search for the impact forces, which is shown on the top left, that once convolved with the impulse responses can give you almost the same, hopefully the spectrogram that is as close as possible to your actual observation. So here now you can, just by doing gradient-based update, by hearing the sound, you can actually infer, okay, what are the moment I hit the object, and how what is the magnitude of the impact as well. So this is about vision and sound. And so, but they are all for specific, single object. Now we have the simulation process, which showed how you can use it for inverse rendering of both visual data and auditory data. So this is only for, again, a single object, or we showed how this can be done for a single object. Then now the question is, okay, we have ShapeNet, which is synthetic, but not as good, but it's large. We have YCB, which is smaller, which is real, which is great, but it has all those real object challenges come with the real objects. So if we want to build a virtualized object set, data sets, by leveraging all these differential simulation techniques that we have just talked about, by doing inverse or gradient-based update on the real observations of real objects, then we should try to have this virtualized data set of neural objects. So that's the idea behind the recent effort we had, also with Jeanette Borg and Fei Li at Stanford, and Wen-Zhen Yuan, who is just moved from CMU to UIUC. So what we try to do is we try to build a data set of multi-sensory neural objects. So the main idea is the same. For every real object, it has some intrinsics, has textures, materials, and shape. So we want to use neural networks or neural implicit representations to overfit and to model these properties. And you can query the neural network with the extrinsics. So what will be the extrinsics for visual data? And that will be the positions you care about, the viewing angle, the lighting conditions. What will be the extrinsics for auditory data? That will be the position of the impact and the magnitude of the impact. And by querying these things, the neural network, which learns the intrinsics of objects and conditioning or the input as the extrinsics of objects, then hopefully the neural network will give you the visual appearance of the objects, the auditory profile of the objects, and the tactile feedbacks of the objects. So the idea behind this object photo data set is a uniform, because it's all sharing the same representation, which is implicit, and neural network parameterized. It's uniform object-centric implicit representations for each object, and hopefully that will be easily accessible to the community as a standard benchmark for multisensory learning. And it will be platform agnostic, so compatible to different robotic virtual environments. So looking a little bit deeper into what so we call every object, every neural network is an object file, because that's the name from the early AI research. So essentially, every object is parameterized by one neural network, or you can think about it as 3 neural networks for 3 different modalities. So the dataset has 1,000 objects, so essentially it's a dataset of 3,000 neural networks. So for every object, what we have is, we have this vision net, which is basically OSF that I just talked about. It is conditioned on 3D coordinates and lighting conditions, and try to learn to parameterize what will be the density and color of the object at particular positions and viewpoints. And you can combine this OSF representation with volume rendering to render images for you. For sound, we also talked about it, right? It's based on diff impact and using modal synthesis. But now the extrinsics are, in addition to the 3D coordinates where the impact is happening, and they also condition on the frequencies and damping coefficient. For touch, which I didn't have to talk about, we actually built on top of Wenjun Yuan's tactile simulator for geosites. So the tactile simulator is called Taxium, but what will be the extrinsics for a tactile signal? And it will still be the positions where I'm touching the objects, as well as the contact orientations, right? To which direction I'm trying to feel the object, and geopenetration and the geopenetrations, which is to think about it as the magnitude, how hard I'm pushing this object. So so that's object folder 2.0, because earlier we had a version 1.0, which is smaller and not as good. So 2.0 had 1,000 objects and 3,000 neural networks. And for all these objects, they're parameterized neural network. You can re-render them from different viewpoints, relight them, and you can use query neural network to get you, okay, what will happen? How would the object sound like? And how would it feel like? One challenge with this neural implicit representation is, especially for the vanilla nerve, because it has to do volume rendering, it has to query a lot of times and do some integration, it's kind of slow. So if in robotic applications, if you're doing even just especially in reinforcement learning, you probably don't want to wait for a minute for the system to tell you, okay, what will be the object, how would the object look like at a particular position. So one thing we did is we also incorporate the recent advances called, basically you just reparameterize the neural network with 1,000 but much smaller neural network, so that the rendering process becomes much faster. So every object in our dataset can be rendered from any particular viewpoint under arbitrary lighting in real time, right? So you don't have to wait for a minute to get the appearance of the object. So here's an example of one object in our dataset. You have a YCB muck, and you have some representation for the materials and the scales, and here the sound that the neural network has learned to encode, and this output of what is going on there. So you can see the object is making slightly different sound if the impact is at different positions. And just to make sure that we're not too far off with the ground truth, so we actually go to a recording studio at Karma, and we hand the object there, and then we hit it with the impact sound, with the impact hammer to record the actual sound the object makes. So you can compare that with the real impact sound recording, and then we have some quantitative benchmarking and analysis in the paper. So it is reasonably close. Of course, it's still not identical, and we're trying to improve it, and we're thinking about ways to actually to close the gap. But I think in some sense it's reasonably close. And here's a different example of a porcelain picture. It's a ceramic, has a different scale, and the sound that it makes. As well as the impact sound from the real recording. Well, so it's not terrible. And for tactile, here are some examples of the tactile responses. If you have because again we use a taxium, which is similar for geosite, right? So of course these images are in geosite format. That essentially you translate the responses into some images but colored with lights from different directions to essentially capture the surface normals. So you feel it, you can see that by touching the object, even at the same position, just by having slightly different orientations, rotations, and different penetration depths, you can see the differences in these tactile responses. And again, these are all parameters of the neural network, so you can just query the neural network, send the input to the neural network. Okay, I want p equals 2 millimeters, and phi is 0 degrees, and it will just output this image for you. Here's a different example of, basically you're touching the picture at a different position. So once you have that, right, what will be the applications? What are the things you can do with it? So we demonstrated a few kind of simple applications, although we're still working on it and try to explore how it can really be used in benefit robotics. But some simple applications are, you can base on tactile and audio data, without seeing objects, you can try to feel it, and then hit it, and based on the sound, you can try to localize, okay, which part am I touching the object? So think about if you're in a dark room, and you try to, figure out, okay, where the object is, and to try to grasp them. So it's like tactile audio contact localization. I'm not going to play a sound because they're kind of similar, but essentially through a few iterations, you feel the objects, you hear the sound the object makes, and then you do a few times, then based on a particle filtering framework, you will be able to eventually locate, okay, what are the positions I'm touching objects, so I can, in some sense, locate myself, the finger, relatively to the position of the objects. And shape reconstruction, multi-sensory, so going from not only a single image, but if you feel the object multiple times using geoscience sensor, you collect all these tactile images, and that gives you kind of some sparse signals, but pretty accurate, I would say high precision, but very local, right? So signals about object geometry, and that can be integrated with visual image. There are a lot of work on going from visual image to 3D shapes, so you can put them together and give you a shape reconstruction. But these are like the typical applications that these data sets can enable. So we're not trying to, we're trying to show that our data set is supposed to be supporting all these applications, although we're not trying to make innovations here on how we can do better on these tasks. And of course, you can also, say if you're trying to grasp an object, based on the tactile images to infer whether such a grasp is successful or not, to guide your policy learning and stuff like that. So these are like the tasks that we care about, and we say, okay, the data set can support all these. And most recently, just this year's Coral, we also try to explore a little more on, once you have the objects and you have all these sensory observations, okay, that's the data set part, then how you're going to better use it, right? Can you come up with a model to better use and integrate all these informations? Due to time constraint, I'm not going to talk about it in detail, but at a high level, we try to integrate all these multi-sensory information, visual, audio, and touch using a multi-sensory transformer based on attention, and we use it to solve kind of pretty complex tasks. It's a bit contrived, just to be completely honest, because we have to come up with tasks that really require 3 sensory modalities just to really show the benefit of this framework. It turned out, right, in most cases in our life, we may rely on 1 or 2, so it's not that common that we'll use all 3. But we try to come up with task setups that could be a bit contrived, but really demonstrate that where there are cases you may want all 3. In dense packing and pouring, I'm going to show just one demo on pouring. Because pouring is something like when I try to make coffees myself, I rely a lot on actually the sound, because sometimes I'm just like watching my phone or something, so I just based on the sound I can say, okay, that's about all right. So this is like what's going on in the real world. Right? You hear the sound, and clearly the pictures are going to change and frequencies, and based on that you'll say, okay, the mark is full, and I have to stop. Right. So now if we want a robot to do similar things for you, and especially in the cases where the container is opaque, so you cannot see the level of water there, then you may want to rely on this information as well. We don't want a robot to play with water, so it's kind of small beads. But actually, this is a bit hard to hear. Let me see. Can people hear it? Probably not. Yeah, somehow this video has a. Let me see. If I can do this. Yeah, first time showing this video, so. Okay, I'll fix it for the future, because it's the first time I'm showing this video. This is very recent, Core 2022. actually, if you can hear the sound better, then you can actually tell, even those are not water, they're liquid, they're just beads, but you can actually hear the difference in the pitch. And the goal here, the robot is trying to complete a task that is trying to pour exactly 40 grams of the beads into that container. So it turns out that by adding the sound information, especially in the cases where the robot cannot see what's going on in the container, they actually really helped, and the robot was able to do it much more precisely. Okay, so finally, we talk about small sensory object. We say, okay, we try to model them, right, by making the simulation process differentiable and using inverse process to capture their appearance and the sound they make, and how we can scale it up into a data set. And some of the applications, the data set we enable, and the method that we can use to leverage all these sensory modalities. So one thing that was missing, what is that? Is here in many cases we assume we have all this amazing ability, which is like a miracle, that we can capture whatever data we want. Right? In the case of OSF, we're like, okay, we can put an object there, and then we can take a lot of pictures of it and condition on different lighting conditions. In the case of the sound, we can say there's a silent room, and then I can hit it with an impact hammer, control everything, and there's no noise and everything. But if you really want this system, the inverse rendering process, if you want to invert this differential simulation process, but you want to make it to work in the real world and to get as many data as possible, as realistic data, as diverse data as possible, then you have to deal with noisy data, because you cannot assume, a lot of things we did, we have a dark room, everything's controlled, we control the light, it's anechoic, we control the sound. But we cannot assume that we have this kind of, dark rooms everywhere. So if we really want to virtualize and build a data set of real objects, then in many cases we have to deal with messy data like this. This is not even that messy, it's pretty clean actually, but still pretty reasonably messy, in the sense that you want to go from noisy, messy observations of there could be multiple objects in terms of visual data, there could be occlusions in terms of auditory data, there could be noises, and objects occluding with each other, objects reflect light on top of each other. So we want to deal with all these things without assuming we have control over everything, but still be able to infer or derive these neural object representations from these kind of more complex observations. So we tried a little bit in exploring, this is pretty much ongoing work and very preliminary, but we tried a little bit in exploring how we can go from these noisy visual observations. This part we only focus on visual so far. How we can go from visual observations to get the underlying neural object models. So we feel like in order to work with real scenes, we want these neural object models, they should, or any methods that infer a neural object representations, the inference method should have three properties. The first one is, of course, we wanted to learn without supervision, right? Because there are a lot of cases where you can say, okay, if I know this is a chair, and then I can annotate a lot of chairs, I can do kind of 3D reconstruction or stuff like that. That's working reasonably well, especially if you have a lot of data. But especially in the applications of robotics, then we often deal with objects we've never seen before. Sometimes you don't even know is that an object category for it. It's just like a random piece of thing. So we wanted to learn without supervision or prior knowledge or assumptions about object categories. I'm not only working with cars, I'm not only working with a mug, but the inference method can derive these object representations without assuming object categories. And you wanted to explain the image formation process, because so what does that mean? It should really capture this generative model, the simulation process. There are a lot of work on going from a single image, I decompose it and try to infer this is a segment, that is a segment, right? So I get a lot of these image patches or segments, but they don't really understand what is 3D and capturing the 3D geometry or the simulation process in terms of visual data, the rendering process. Then what happens is, you get these segments, but you don't really know, especially in the case of occlusion, or if I remove an object, what am I going to see? Because you don't capture image formation process, and every object to you, it's just like a piece of paper, and often occluded, a partial piece of paper. So you really want to understand that. And of course, you want to also be 3D aware, so you capture the geometric and physical properties of objects in 3D. So if you look at what existing methods can do, right? So this is in computer vision back in 2013 without deep learning. People can okay, given me a collection of images, I can try to give you the segments of these objects. So they're unsupervised, they don't assume object categories, but they're not really 3D aware. Again, these are like pieces of papers, and they don't capture the image formation process. So how the image is made, So more recently, there is some work, especially from DeepMind and Google Brain, where they try to use, most typically they call it slot-based methods, which is essentially trying to use neural network, combine them with probabilistic inference framework to infer, going from a single image, okay, what would be the objects that can belong to these different slots, with the hope that different slots will correspond to different objects. So these models are also unsupervised, and in some sense they do, sort of have a little bit knowledge of the formation process, because they're like, okay, the image is made because they're objects, and they're like, there's like a probability distribution. Actually, they have a probability, you can call it like a probabilistic image generation model about how this image can be synthesized. But they're not 3D aware, so to them, these are like still like 2D parts, and you cannot imagine how the object look like from different viewpoints. They don't capture anything like 3D geometry of the objects. And there are also other works that are trying to directly reconstruct the 3D geometry and pose of the object, so that you can change the object positions. Given you an image, you can get the positions of the object, you can move the object around. So these kind of work, they do understand, yeah, it's 3D, and it does capture everything like rendering and everything. But most typically, these kind of work, they assume, and I think the most typical one is they always assume they work with street views data. So because they know the only object category that they can work with is cars. This is because they require a lot of annotations of the object categories. They're like, okay, for this object, what would be the geometry? Or for all the cars, what would be the mean shape of the possible cars? So they assume you have knowledge of object categories, and they're not like unsupervised, and they cannot really generalize to new objects. The market is not like new objects, but these kind of new objects here and there, which I don't have that many 3D CAD models for. So we thought, is it possible for us to do this kind of unsupervised object discovery, but discover these neural object representations that hopefully captures all three aspects, right? We wanted to be unsupervised, we wanted to explain the image formation process, we also wanted to be 3D aware, so that you can remove an object, seeing what's behind, but you can also rotate an object, seeing the other side of the object. So here's what we can do is, going from my input image, again, this is all without supervision, and doing testing, the only input is a single image. You can actually get different segments, or actually different, I would say not segment, different like slots or different entities that you capture, okay, these objects, and as well as the background. And you capture them in 3D in the sense that you can rotate object and see what's behind, and you can reconstruct the scene, you can remove an object, you can insert an object, and you can rearrange the objects. So the inference process goes this way. Given an image, we do use this kind of slot-based approaches, which is something I talked about earlier, but they work with 2D. So what we took their inference framework about decomposing objects into a number of different slots, but then instead of directly reconstructing the image, we incorporate these kind of object-centric neural representations. Say for every object, think about it as a conditional vector, and you have a neural network that is conditioned on it, and you decode, okay, what does that vector really represent, right? So you're able to decode the geometry and the reflectance of objects based on, but now you have a conditional decoding model, so which is not overfitting to a single object. Before we say, okay, we overfit to a single object folder is a data set of 1,000 objects, we have 1,000 or 3,000 neural networks. But here, it is kind of a bit more general in the sense that, okay, we have different neural networks, but actually we have two different neural networks, one for background, one for foreground. But for these neural networks, they are conditional in the sense that they take the latent vectors that hopefully captures the geometry and material and reflectance of objects. And you're able to decode it once you condition on this latent vector, and then you still query the XYZ, the positions and viewpoints and everything, and you will be able to get different objects with this conditional neural network. So once you can decompose the scene into different slots or different entities, and you can decode their appearance in 3D, then you can put it back with all these standard image rendering framework to reconstruct the scene, and your training is unsupervised, and so which means on the supervision you have is how well your reconstruction is doing. You try to reconstruct the scene, you compare a reconstructed image with the input image, and in training, we do assume you have multiple views, just like NERF. So you can reconstruct the image from different viewpoints and see how the reconstruction look like in different viewpoints. And during testing, you're only given a single image, and you can infer the segments and do normal view synthesis and editing as well. So here's a bit more results. Input view, and this is the ground truth. The second column is the ground truth segmentation, and this is purely using slot attention, which doesn't have this kind of object-centric modeling, doesn't use neural object representations, does not capture things in 3D. So first, it doesn't work that well, and second, because it's not 3D aware, it cannot synthesize what's going on from a different viewpoint. And this is our results. This is like a comparison with the baselines. And we did want to see how well it works in real images. So clearly the model is still limited in how the complexity of data it can deal with. So before it was all synthetic. So we were like, can we capture some real images? So again, we purchased some objects and we capture these kind of images of real toy chairs. And it does work on generalizing to these real toy chairs, but that's basically this paper can do. That was with Leo Gibas in this year's iClear. So it's I think it's okay, but there's still a long way to go about going from these synthetic toyish data, either in actually this is real data, but it's contrived. I would say contrived synthetic or real data to the actual complex scenes that we care about. But the benefit of this kind of representation is, once you can do that, you can, I would say, moving an object, as we showed before, this is like ground truth. If you compare with the baselines, they can't really move an object. They don't have the knowledge of the 3D representations, and this is you purely using just nerve with an autoencoder, and the last column is hours. So you can actually remove an object. You can see an object from different views. You can change the background. So you say, okay, I have an image like this. If I want to change the background so that I want everything else to be the same, but only the background of this input image should be the background of that image. So these are, you can also do much better than the baselines. Okay, so we do care about generalizing to complex scenes. So finally, let me wrap up with our very recent, this is mostly ongoing effort about how we can generalize for this inference method to infer these neural objects, not only from images of synthetic pure color chairs and real chairs, but still very simple chairs to slightly more complex scenes. And I think we observed that the biggest challenge of scaling this method up to more complex scenes is when you're trying to infer the objects or decompose it into different slots or entities, because we're purely based on earlier work called slot attention, and it doesn't really generalize that well to more complex scenes. So we need methods that, and the reason that didn't generalize that well is it is trying to infer, okay, what is an object purely by reconstructing the scene. So it's purely based on appearance cues. Therefore, it works well or relatively well for objects with pure color, but for objects with more complex textures, and it doesn't work that well. And also, this is not really how objects are made, because if we think about what is an object, it's not like of course it's likely that objects, a single object, different parts of a single object may have similar color or appearance, and that's why these methods work to some extent. More importantly, what makes an object an object? Also, if you're looking to classify this quality of science, they're like it's more about their motion, right? The way they move together, and under the same interaction, these different pixels they move together. That really makes them an object. So if we care about the problem of, now we know that the problem we want to solve of scaling these inferring neural object representation work to complex scenes is to actually address the problem of the first step, that is unsupervised category-agnostic segmentation of static real-world images into objects, because once you can do a segmentation, you can do a conditional neural object representation nerve to infer the objects in 3D and re-render. So if you care about this problem, and this is a demo of the, not demo, this is a data set from, this is the bridge data set, right, collected by people at Stanford, Berkeley. So you can see that our goal is, based on object motion, you will be able to see, okay, what are things that actually often move together, and you can tie these object motion to their appearance, so that based on a short video of what object has been doing, you can infer and to do segmentations, you can get the segments of these different objects. Again, you don't assume supervision, you don't assume annotations and object categories. So the goal is this is purely unsupervised, and this is category agnostic. So this is the main idea behind Eisen. So our joint work with Dan Yeamans and actually also Josh Tenenbaum as well, as Mark mentioned, with also Dan's students and postdocs, Hongling Chen and Dan Baer. So the idea is a collection of physical stuff will always move together under the same application of everyday actions. So can we actually leverage the fact that things that often move together based on their motion, in addition to appearance cues, to discover what makes an object so that we can get unsupervised category-agnostic object segmentation. So, unfortunately, I don't have time, and there are only 4 minutes left, and people are leaving. But so I'm very happy to talk about it offline. But here I'm just going to show one slide of the results, where here are the input images. Again, actually, one thing I forgot to mention is during training, the framework, which we call Eisen, leverage motion to learn what makes an object, and try to tie object motion information to the appearance. During testing, it actually, because it has learned what are the textures of objects that often move together, during testing it only requires a single image. So it's learning unsupervised category-agnostic object segmentation from a single image. And here on the left is the input image, and the second and third column on the baselines, and the fourth column is the Eisen output. You can see that it does pretty well on unsupervised category-agnostic object segmentation for these kind of pretty complex scenes. And there's still a gap between that and ground truth, but I think it's actually pretty close. I was very impressed by the results of this paper. Then we thought, okay, of course, now you address the challenge, not fully, but to some extent, address the challenge of how you can get unsupervised category-agnostic segments of the objects, even from a single image. Then you should replace slot tension with Eisen, right? So now you give an image, you do the same thing, and try to get the object segmentation based on Eisen now instead of slot tension, with the hope that it generalizes to these more complex objects beyond just pure color chairs. And after that, you can do the same thing as we did before, decompose every object segment into a conditional latent vector and decode it with, conditional, I would say, neural object representations to get object nerves and background nerves. And you can put them together to reconstruct the scene. And again, you can train to reconstruct the scene by matching the reconstruction loss. Right? So here, the same pipeline as before, but now the inference of neural objects relies on Eisen instead of just slot tension. And finally, we were able to make a little bit more progress on how you can get these kind of 3D-aware, category-agnostic, generative representations for slightly more complex scenes. So these are beyond, pure color chairs. And you can go from images, and this is the method we had before. We call unsupervised object radiance fields, so it's like UORF. For these more complex scenes, because it's purely based on textures, it didn't work that well, especially for objects of multiple colors. But with what we call this motion or moving object radiance fields, morph, then it does much better, and it's reasonably close to the ground truth. Again, this is going from a single image, and discovering the objects, imagining how it looks like from different viewpoints, getting that 3D neural object representations, and re-render it. So this is the input image, and the output is re-rendering the image from different viewpoints. You can compare that with the ground truth. So it does, I would say, reconstruct fine-grained photometric details with higher fidelity, and it also captures object geometry. Again, this is all from a single image during testing. These are novel objects. The system has never seen these objects before, and also there's category-agnostic. You can see these are objects of different categories. Again, from a single image, it can do reasonably well in getting the geometry objects, perform novel view synthesis, reasonably close to the ground truth, and much better than the baselines. So I would say it also allows faithful mesh reconstructions from object radiance fields. Okay, so to summarize, I have 1 minute left. Now we talked about modeling, how we are making the simulation process differentiable and inverting the process so that you can get object-centric representations, often parameterized neural networks for its visual appearance and the sound. The data sets, how you can scale it up so you can have a data set of 1,000 neural objects or 3,000 neural networks, how it can be possibly applied into these robotic applications, as well as the inference problem, how you can infer these neural object representations in the case of cluttered, messy scenes. Now this is pretty much ongoing work, as you can see, but we're making progress. So if I want to summarize the key message I want to deliver in this talk, I think it's mostly about, sure, it's very popular to have implicit or neural representations these days for modeling nerve and scenes and everything. And people say, okay, that's great, so we can look into how they can be applied not only in vision and graphics, but also in robotics. But I think when you're doing that, you may want to think about, what are the things that should really be learned or parameterized by neural networks, and what are the things that are already there, and there's no need to, either relearn it, or, learning it may not help you, but actually hurts your generalization. Now I would say what we're doing here is we're thinking about the physical object models, right? So what really makes an object an object? What really belongs to the object? What are the object intrinsics? And these are often the things that are complex, hard to model, I would say analytically. So probably should better be learned by a neural network. And by having this right level of abstraction and disentanglement, then allows you to do flexible and compositional generalization in terms of, seeing scenes with multiple objects, but with different rearrangement configurations or under different lighting conditions. And once you can infer these object representations, you can move the objects, you can imagine what's behind, you can see it from different views, and stuff like that. So I think fundamentally we want to address the questions why, that is, when and why is the reason to use implicit representations or neural representations, and when to use it and when not to use it. Right, so I think these are like a summary of our approach, leveraging these kind of powerful neural object representations, but to deploy it in a physical object-centric way to get these multi-sensory neural objects. Thank you.
I enjoyed your slide combining tactile and vision, of course, because I do tactile stuff. But a question I had is, do you think there was any information you were getting from the tactile sensor that was
not visible,
more useful than just having like a camera on the finger looking in and having another camera that would also provide more information? Would that be just as good?
Yeah, that is a very good point. So I think if you're looking at this like the reconstruction part, that this is like a 3D shape reconstruction. I think probably not, because again this is a demonstration of like, we have 3 modalities to support these tasks. But this particular example, I don't feel like you actually maybe touch really giving you more. But if you look at later work where we try to really show there are cases where tactile information can be useful. And I feel like this is the task that I didn't talk about called dense packing. So in sometimes you're trying to insert objects and put them together, and then, but in a very compact way. And I think these are cases where we do have a lot of ablation studies as well as the visualization of the attention maps of neural network to show that there are cases where the neural network really rely on the tactile information to really get object to the right positions.
Yeah. Okay. Thank you.
Thank you very much for the talk. I had a question about how easy or difficult it would be to update your object dataset 2.0 as you refine your techniques for learning different types of sensory interactions with the objects.
So you're saying, sorry, just try to make sure I understand the question. Are you saying once we have a better simulator, like TAXM 2.0 or something, then we have better tactile sensing or better auditory simulation as well, then is it possible to update the data set so that the representations can leverage these advanced simulation techniques so that they are more realistic? Is that your question?
Yes. Yeah, exactly.
I think yes. I think that is actually sort of the benefit of these virtualized data sets, because if you have a YCB set of YCB objects and one of them is broken, what can you do about it? If you try to get a replacement, that seems hard, and that object may be out of stock or something. But for these virtualized objects, I think the benefit is once you have better simulation techniques, yes, you can get better representations of the objects' acoustic or tactile properties, and all you need to do is to retrain this neural network. So you can just release an updated neural network that everyone can use, and the neural network output is just more realistic. So, if that is your question. Yeah.
Yeah, no, that was it. You don't need to do more sort of ground truth testing.
I think no, yeah, because yeah.
I guess there's been many recent work on using a nerve to learn representations for robot manipulation. So I guess also some work learning for like articulate objects using a NERF. So I guess, do you see NERF as a future representation that's going to be super helpful for like manipulation tasks? Or do you think like other representations like a key point or like a density descriptor set could be more useful for manipulation tasks in particular?
I think it's very interesting that, and your question is a typical example that because NERF give this amazing visual quality, then people use it to refer to something else. Because when you say NERF, I think you're not really referring to NERF in particular, because that is a method that for non-view synthesis, and allow you to see an object from different views. And the most impressive part of NERF is the objects that look so realistic, details you have all these textual details. But is that something you really care about in robotics? That is maybe not. And I think what you're really seeing is, what about neural object representation, not the radiance part, not the nerve R part, but what about, if you look at, what is maybe more critical to robotics is, in particular, I would say geometry. So the idea of using neural network implicit representations is way there. Like 2 years ago, then there's DeepSDF and all those work that they have been showing the power of these implicit representations. It's NERF that they say, okay, instead of using it for geometry, we use it for radiance. And that gives you this fantastic visual quality, just like DAL-E these days, or earlier CycleGANs. And suddenly it got so popular, everyone's talking about it. But the underlying, I think the most important idea is to think about it is to use neural networks to parameterize some key properties that we care about. And I would say it's less about NERF, it's less about radiance, and maybe more about geometry, maybe more about physics. It could be the neural representation for object physics. And now, if your question is not about NERF, but in general, would neural representations play an important role to capture these important properties, and how would that compare with other explicit representations like key points and meshes? Then I would say yes. Probably at least I can imagine a combination of these explicit and implicit representations will be needed, because there are a lot of things that we don't really know how to parameterize explicitly, and all we have is a lot of observations. So it's more like a data-driven approaches that you can overfit to the data by a neural network for things you care about, and you cannot really write analytical equations for. But probably that's not radiance, or radiance is very secondary.
Thank you.
Do you think it might be useful to simulate the sound of two objects interacting with each other? And if you have the impact response of two different objects, the auditory impact response, can you go from that to what it would sound like if they hit each other or they rub against each other?
I'm sorry, I didn't get the question. So you're
like
saying
if you have
for two objects, we have the impulse responses of the two objects?
So you have the separate responses of the two objects when you hit them with an impact hammer.
Right.
But if you want to simulate what happens if you rub them against each other, for example, a cup on a table.
Yes.
Do you think that might be useful, and how difficult would it be to go from the individual responses to also being able to simulate interactions between them?
Because essentially what is going on is, if you have two objects colliding with each other, if you drop something on the table, then it's basically, you think about it as, there are things that we cannot simulate, but in most cases, there are a lot of things you care about. It can be decomposing into a number of impacts at different impulses, at different times, at different time steps with different magnitudes. So in the case of two objects colliding as well, there's probably one collision happening, a lot of collision happen later, subsequently over time, they're not as large. So I don't see why the method cannot be extended there. There are things that are really hard to simulate, like the sound of scratch. I don't want to scratch, it sounds bad. But if you scratch a blackboard, those are kind of slightly different, and that's very hard to simulate. And I don't think, because all these things we build on simulation techniques that are mostly developed in computer graphics, that are ongoing work. And Doc James at Stanford is he's a very major person who created all these techniques. And I think a lot of sound like scratches we still cannot simulate very well, but for impact sounds we can simulate pretty well. And it's nice that for a lot of manipulation problems, especially involve rigid bodies and deformable objects, not deformed, articulated rigid bodies, you can actually decompose a lot of these into just impact sounds. So that's what we can do.
Thank you.
I was just wondering, so when you were showing that example for like audio, when you were pouring the water,
Right.
how that would work if you were to unify that framework with a vision capability, right? Like I see you have this last slide, but we weren't able to get to it due to like time constraints. Because like here, the amount of sound you have like largely depends on how much higher above the like cup you pour it from. So then that could depend also on like vision, you realizing like what position is best to hold it at to then
I think the sound you make is actually based on the container, the tube, because you can think about it as there's air here, and when you fill this up, just like pouring water, when you fill this up, then the amount of air becomes shorter, then the pitches will change. So I think that's probably mostly independent of where the arm is. But it does matter, where the microphone is. If you put a microphone on an arm, then if you're very high up, the microphone can get very little sound. But I think in this case, we probably put a microphone here or something. Yeah.
I see. And then how does it work when you unify the three frameworks? Like at the end, when you unify all the senses, how does it end up working out? Is there, do they interact well with each
that's
other?
very interesting. There's a slide, it's already too long, so I removed a lot of slides. But we do have some analysis in the paper to show, that you try to, at different stage of the pouring process, the system may, at the very beginning, it may attend mostly to vision because there's no sound, and you want to make sure that you're at the right position, you're right above the tube. And when it started pouring, it's actually more important to look into the other two directions because there are some actually here we try to there's a visualization, but in practice the camera cannot really see what is inside the tube. I think there's some tape, so it's kind of opaque, so you can't really get much from vision. You have to rely on audio and touch to sense and to hear, okay, how much have I filled the tube, and then especially at the end, I think the system put a lot of attention on the sound when it's close to the moment that it should stop. But there's a plot, but I don't have it here. Sorry about that. Yeah, but it is in the paper. Yeah.
All right, probably we should close this session for now. Thank you again.
Thank you.